Okay, I'm going to run through the answers to this relatively quickly. I'm going to do what everybody should always do and list some things off to the side before we get into the solving part itself. And go from there. So, car has a mass of that. It travels from rest to 40 meters in 3 seconds. This is not a speed. This is how far it goes. So this is our delta x, and this is our time. This is our mass. The car is accelerated uniformly. That means that acceleration is constant. It gains speed at a constant rate. So find the acceleration and how big is the net force. So part A, using the kinematics to find the acceleration. What do we know? We know a delta x, and we know a time, and we know a v initial. So v initial is 0. Delta x is 40 meters, and t is 3 seconds. Okay, so with that, we don't know a v final. We need to find the a, and we do know v initial, so we can't use anything with v final in it. And so from the list, we can rule out ones that don't have that as a given. I paused this recording for a moment and I wrote up the kinematic equations list over on this right hand side of the page. You should have that list in your notes, but for now I wanted to reference that because we can't use any equation that has a v final in it. So I can't use the top one. I could use the second one, but it's kind of ugly. I can't use the third one, can't use the fourth one, can't use the fifth one, so I guess we got to go with this one. Okay, so plugging the numbers in, the 40 meters is the delta x, the v initial is 0, so that times time is really going to be 0 for whatever we put in for time, and this plus 1/2 the a, and the time squared, the time is 3. So now we just do the math. So this is going to be 40 equals 1/2 times a times 9. So if I do the math, multiply both sides by 2 to get rid of this half. So 2 times all of that cancels the half. 2 times that is going to be 80 equals 9 times a. Just flip-flopping the 9 and the a around. So divide by 9, divide by 9. And it's going to be just a little bit less than 9 because 9 times 9 is 81. 80 over 9. And if we do that real quick on our calculator, we get 8.888 repeating, so I'm going to call it 8.9 meters per second squared. So there's my acceleration. And now in part B, okay, forget it. In part B, F net, when it gets to talking about forces, we go to the F net equals ma equation. We can't do anything with forces with just the kinematic equations because they don't have anything to do with force. But how big is the net force acting on the car? All we have to do is take the mass of the car, 710 kilograms, times the acceleration, 8.9, and 710 times 8.9 is 79. That is not right. Pause to recalculate. Is 63 19 newtons. Going on to the next question. A 1,000 kilogram car and traveling at an initial speed. So this is what it's going at beginning. V initial is 25 meters per second. The miles per hour is only here to go, oh, 25 meters per second is like that speed in our world? Okay, cool. We'll go with the 25 meters per second because everything is in the metric system in our little science world. Brakes can apply a force of 5,000 newtons. And how far can we expect this to take to get us to stop? So that tells us V final, if we're going to stop, is 0 meters per second. So I got an initial speed, I got a final speed, I got a distance that I need to find, and I got a braking force. What does this do for us? Hint, make a force diagram and then write the force equation. So let's assume that our car is moving to the right. That's always my favorite direction for things to be moving, with an initial speed of 25 meters per second. And how far is our delta x if our V final is going to be 0 meters per second? So the idea that they're giving us a force to work with might have something to do, and a mass might have something to do with finding a value for our acceleration. So listing these things along with the other things might give us a clue that F net equals ma might get us where we need to be, because we have the braking force, we have the mass given, and we could easily solve it for A. So it says to use a free body diagram to do this. So force from the brakes, you got normal force, you got force of gravity. If I'm going to stop, I'm going to take my foot off the gas, so there's no forward force in this diagram, and that just tells me that F net is the braking force equals ma. So 5,000 newtons, and the mass is 1,000 kilograms. We like nice round numbers that are going to be easy to divide. So if I divide both sides to solve for A, I get 5 meters per second for an acceleration, 5 meters per second squared. Okay, this is to get us to be able to find delta x. So we've got a certain number of things to work with here. So we've got these kinematic equation variables plus the one we just found. Now, what equation can we work with? We still, well, we don't have anything for time. So because there's no time given, we've got to use an equation with no time needed. Okay, there's really only one of them, and that's the V final squared equals V initial squared plus 2 times the acceleration times the displacement. We're looking for the displacement. So solving for delta x, V final squared is 0, so 0 squared is still 0. V initial squared was 25. The acceleration was 5. So the first thing we have to do is move that over there. So 25 squared is 625. And then we have 10x. So if I divide this, it's negative 625 divided by 10 is 62.5, and that's meters equals delta x. Well, what in the world? If we were moving to the right, like my picture shows right here, moving to the right, then shouldn't my displacement be positive? If I'm moving to the right, what did I forget? Well, I forgot to, this is going to change every color. Of course it is. I forgot to add the following. I forgot to add a negative sign. Bailing out on that, I'm going to add a negative sign to the acceleration. Maybe that will work for me. Why a negative sign to the acceleration? Because my velocity was in the positive direction. Nope. Velocity was in the positive direction, but my force was really in the negative direction. This force here should have been thought of as in the negative direction. So if I put a negative in there for the force, then I get a negative. 5,000 divided by 1,000 is negative 5. And if I would have put the negative in where the A went, then I would have been dividing negative 625 by negative 10, and they would all cancel out, and then my distance that I move would be positive 62.5 meters as I'm slowing down. Okay, last question, or is it? Oh, second to the last question. Person is going to dive into the water. So platform is up here. They're standing on the platform. They dive into the water. And so when they hit that water, they're going to have some speed just before they hit it. So that's part A. We can assume that the initial velocity is 0 as they kind of drop off the diving board. The gravity, we're going to use this 10, and it's down. So the acceleration is from gravity. We're going to say negative 10 meters per second squared. Or wait a minute. I'm going to say, let's just make everything downward the positive direction. So forget the negative sign. So call the acceleration downwards positive 10 meters per second squared, because that makes our final speed positive, it makes our displacement positive downwards, and it just kind of like eliminates some of the mess of negative signs. V final is what we want to find. We don't know time. We know that the height, we'll call it delta x, even though it's up and down, we'll call it delta x, is 10 meters. And with that, it's just like the previous question. Really, the only way to go with it is V final squared equals V initial squared plus 2a times delta x. So V final squared, the initial was going to be 0 anyway, so 0 squared doesn't even need to be in there. Plus 2, gravity is 10, and our height is also 10. So V final squared is 100 times 2, 200. But remember, there's that squared there, so V final, we've got to take the square root of both sides. So the square root of 200 is 14.4, if I remember off the top of my head. Checking real quick. 14.14. So I'll just call it 14.1 meters per second. Go away box. So now we change gears and we are hitting the water, slowing down in the water, and this time, so if the water level is here, and we're going to come to rest somewheres down here, and it says that distance is now 4 meters below the surface. We want to know what our rate of acceleration is as we go through that. Remember, we just found the speed that we hit the water at to be 14.1 meters per second. That becomes our new V initial. And V final now, as we drop down into the water, is going to eventually become 0. And A is what we want to solve for. What else do we know? Anything? Calculate the acceleration. We don't know time. We do know delta x. Again, think of everything down as positive. So initial velocity is positive. Distance, displacement, as you go into the water, slowing down is going to be positive once you go under the water. And we want to find the acceleration. So this time it's a little bit different. We can use the one kinematic equation that was, no, we can't because we don't have a time. Well, if we don't have time, we know we really only have one option, and that's the V final squared equals blah, blah, blah. So V final this time is 0. 14.1, oh, if we think about it real carefully, we just took a square root of 200 to get to 14.1, so that's going to turn back into 200, plus 2 times A times 4 meters. So 0 equals 200. If I don't do the rounded off number that I got off my calculator, it gets back to exactly 200. And algebra reminder, everybody. Oftentimes, so why did it turn to blue and didn't turn everything else to blue that time? Don't ask me. That's the bane of my existence with this little tool. You got to do this minus 200 to get rid of that before you can do anything with that 8. So that cancels on that side and it becomes minus 200 over there. And 8A. So divide by 8 now. Divide by 8. And that's going to be 50. 200 divided by 4 is 50. It's going to be 25. So minus 25 meters per second squared equals A. Why did I get minus on the 25? I got minus on the 25 because the acceleration points upwards. If our velocity was downwards, the velocity is in the opposite direction if I slow down. And we were calling velocity in the downward direction positive, so the upwards direction has to be negative, and that's why we got a negative on the acceleration. So that is the right sign for the acceleration. Okay, now the easy part. What is the net force from the water during this acceleration? The mass was given to be 65 kilograms in the original problem statement. We just figured out that the force from the, or acceleration from the water is 25. So all you got to do is multiply them. Now I'm going to pause and do that real quick. Okay, calculator tells me that's 1,625 newtons. And that negative sign still is in existence. So it's negative because that force from the water was up, causing the diver to slow down as they sunk into the water. The force pushes up to slow them down. And up must be negative if we called everything else positive for the downward direction before. So finally, last but not least, this person in my always driving the car forward example is going to try to restrain this child, and so they're going to have to put the force to hold the child in the reverse direction to stop the child from moving forward. So that's going to come into play down there, but that's just thinking ahead a little bit. Calculate the acceleration. It says that the car is going to stop in 0.1 seconds. The car's initial velocity is 13.3 meters per second. Final velocity, if we're stopping, is going to be 0. So we get a little bit easier work here. Calculate the acceleration. So we could use the A equals V final minus V initial over T, and plugging things in, 0 minus 13.3 divided by 0.1 is going to be 100 negative 133 meters per second squared. Negative because I'm calling the forward velocity positive, the positive 13.3. Moving forward to me is the positive direction in this problem. That's how I'm defining it. You could make everything flipped around if you wanted to for your solution, but your sign would just be the opposite at the end. So the acceleration is in the opposite direction of our motion, so that points towards the left in my picture, and the left direction would be the negative direction. So the negative acceleration. So if that's our acceleration, the force on the child that we have to try to produce would be the mass of the child times the acceleration of the child. And if this child is a 25 kilogram child, about 55 pounds, pretty big kid to hold on your lap, I suppose, if you're driving in the car, but you know, people do weird things sometimes. So 133 meters per second times, or meter per second times 25 would be 3,325 newtons. Okay, that sounds big, but how big is that? We'll find out in a minute. The weight, remember, weight is another name for the force of gravity, and if we do the m times g thing, it becomes 25 kilograms times the 10 newtons of force on every 1 kilogram of mass of the kid. So the force of gravity, the weight of the kid, is 250 newtons. And now we get down to, okay, so what does this answer from up there really mean? If 1 pound, so if we were to think about taking 3,325 newtons and convert to pounds, could I lift whatever that is equal to? Could I bench press it? Whatever. That's the idea here. So to do that, we would divide by 4.45 newtons as a conversion factor from pounds to newtons or back and forth. So 3325 divided by 4.45 is 747 pounds. So to stop that kid from moving forward, your muscles would have to exert 750 newtons worth of force, basically 747, but close enough. You know, of course, that is pretty unrealistic. So that's not going to happen. If we did the same thing for the weight of the kid, 250 divided by 4.54. You don't have to know this conversion factor, but the kid's weight just alone is about 56. I said about 55, but that's only because I know that there's a little over 2 pounds to every 1 kilogram. You don't need to memorize numbers like this or the 2 pounds, but as a ballpark idea, if you know that 2 pounds is basically 1 kilogram, 1 kilogram is literally a 1 liter bottle of water. So you know what 1 liter bottle of water, like a Nalgene, big Nalgene 32-ounce thing, that's about 2¼ pounds. So if you want to convert that or have a ballpark idea of what that means in converting problems like this, just think a 1 kilogram is roughly 2 pounds for a conversion factor. And that's about it.